Volume change during the reactions occur primarily in the gas phase reactions, not necessarily limited to gas phase reactions, but primarily. So we are going to take an ideal gas mixture and we are going to take the effect of temperature, pressure, and also the change in the number of moles on the overall volume of the reactive system. So let us take a symbolic 2A going to B type of a reaction. When we start from 2 moles of A, when the reaction goes to completion, we have only 1 mole of B left and 1 mole equivalent has disappeared. This is going to have a reflection on the total volume, and we are going to learn how to take this into account. The most rigorous way to take this into account is by preparing a stoichiometric table. Again, let's start from the species. Initial, change, and final. We have species A, species B, and of course we are going to reduce this reaction to A going to 1 over 2 B to have A with unity stoichiometric coefficient that helps us carrying out mathematics a little bit more easily. So initially we have Na0 in a batch reactor, NB0. The change that occurred during the reaction is going to be minus Na0x. And in the final situation, we are going to have Na0 minus, or Na0, 1 minus x, many moles of A. As far as B is concerned, the change in B is going to be plus 1 over 2 NB0x. And this is going to be Na0 times theta B plus 1 over 2 x. Now let us see what we have started with and what we are going to end up with. Initially we had N total 0 to be equal to Na0 plus NB0. At the end of the reaction, we have Na0 times 1 minus x plus theta b plus 1 over 2 x. So let's separate the terms with x and those without. We have Na0 plus Na0 times theta b, that is equal to NB0. This is NT0. And here on the other side, we have Na0 times x times 1 over 2 minus 1. So this was the stoichiometric coefficient of B. I will call this nu B. This is the stoichiometric coefficient of A. I will call this nu A. This is nu B minus nu A. Actually, this is nu B plus nu A. The stoichiometric coefficients, as we defined, are positive for products, negative for the reactants. So the stoichiometric coefficient, if it is for a reactant, is going to have an inherently negative sign. So this term is called the delta. All right? Delta is a new term that we are defining. It is the net stoichiometric coefficient of all the components in a reaction. So, in a concise form, this expression is NT0 plus Na0 times delta times X. Now I'm going to take this into NT0 parentheses. This is going to be 1 plus Na0 over NT0 is the initial mole fraction of A. I will indicate that as Ya0 times delta times X. And as you can see, if delta is positive and total is going to be larger than initial and total, as if delta is negative and total will be smaller than and total 0. All right, so this is about the number of moles. Now let us use the ideal gas law here. Let's divide the board so that our derivations do not blend into one another. So we are after volume, right? According to the ideal gas law, P times V is equal to N times R times T. So we have a beginning of the reaction. Let's label this as time 0. And we have the end of the reaction. Let me put N total here also. So we are doing this analysis for the whole reactor. So we have at the end of the reactor, P times V is equal to N total times R times T. Now we are curious how this is changing as the time or reaction progresses. So we are going to divide 2 by 1 to obtain V over V0 is equal to N total over N total 0 times T over T0 times P0 over P. It transfers P terms to this side of the equation. Or V at any time or at any progress of reaction is equal to V0 times T over T0 times P0 over P times N total over N total 0. N total over N total 0 is this term. 1 plus Ya0 times delta times X. This term is frequently called epsilon. Now we have an expression that we can use to take the volume change into consideration.